Well, good afternoon. This is 2:37. We're 7 minutes late getting started. Sorry about that, but I had people from my last class asking me questions at the end and made me late getting down to try to finish lunch, and then I got stopped in the hall twice on the way down to try to finish eating lunch. So just running short of time today. Sorry about that. We'll do the slideshow from current slide. And let me go over a couple of announcements just to let you know where things are. Now, first, I think I told you last week that I was out last Friday because I had to go to a state meeting. We're doing curriculum review for I was doing for two courses. Most others had one, or one group had three courses to do. But I was doing for linear algebra and differential equations. So I had to be down in Opelika, and we had to leave here at 6 in the morning to get there by 9. And then the meeting actually got over early, around 12:30ish, and so we were able to get back here by about 3:30, which still made a 9-hour day. And normally my Fridays are supposed to be 4-hour days, so I asked if I could have this Friday off because there's some things I couldn't get done last week that I really need to take care of. So I will be off again this Friday. Sorry about that, but just got to happen now. So anyway, that's the one major announcement there. Not that major, just in case you're looking for me next Friday, I won't be on either campus. The other is just something looking ahead a little bit. Summer schedules, I don't know what's going on with that. I've heard so many different rumors and nothing official yet. I hope to find out after this class what in the world we're doing this summer. I've heard that we're moving from a 10-week summer this summer only to an 8-week summer this summer only, and also going back to either a half day or a full day on Friday, but no classes on Friday. It's just all over the place what the rumors are, and they've basically been started by the administration trying out different ways to make the summer work, and none of the solutions are sounding very good to me. I've got to find out, because we're supposed to have schedules done by the 1st, which is a Sunday, which is bizarre, but they haven't told us what the parameters are yet. They've told us one thing, but that doesn't make any sense, so I'm trying to get a good reading on that. So anyway, don't expect the summer schedule to be out quite on time. If it is, mine probably won't be accurate because I don't even know what's going on yet. So anyway, that's the other, I guess, sort of a major announcement, but not a very good announcement. I'll put it that way. All right. Anyway, we're in Chapter 2, which is first order differential equations. We're in Section 2.4, exact equations, and this is we got started on it last time, just sort of introduced it, got down to the definition, so that's probably a good place to start today. What do we mean by an exact equation? Here's what it is. Let me get my pen set up. Kept thinking some students would come in, but no one has yet. A differential equation, DE is differential equation, that's written in this form: m of xy dx plus n of xy dy is equal to 0. No, I'm sorry. Just an expression. This isn't an equation. They say it is, but it's not. A differential equation that looks like that. I'm sorry. They said it correctly. I said it wrong. They said a differential expression, because I was going to say that's not an equation. A differential expression, okay, m of xy dx plus n of xy dy is an exact differential okay, in a region R okay, of the xy plane my pen's getting caught on things. If it corresponds to some function f of xy defined in R, that same region R, okay, period. A first order differential equation of this form why I did that, I'm not sure. Of the form m of xy dx plus n of xy dy is equal to 0 is said to be an exact equation if the expression on the left is an exact differential. Okay. Now, what this is saying basically is they really throw the words out there. Seems like just enough to get really confusing. So a differential expression, m of xy dx plus n of xy dy, is an exact differential on some region R in the xy plane if it corresponds to some function f of xy defined on that R. So if that refers to f of xy, then that's called a differential expression. Okay? To be a differential equation, then that differential expression that corresponds to some function f of xy, that is equal to 0. Okay? And here's an example of this. Let me go to a clean page. X squared y cubed dx plus x cubed y squared dy is equal to 0. That's an exact equation because the left-hand side is an exact differential of this. F of xy is equal to 1/3 x cubed y cubed. Okay? Let's see if that's true. If you take the partial of f with respect to x, okay, I'll leave off the f for now. Okay, we're going to come back and name the f. Okay, but that's an exact differential, if you do the derivative of this, okay, that would be partial of this thing with respect to x dx plus the partial of that thing with respect to y dy. That makes it a partial derivative, I mean an exact differential. And let's see if that's true. The partial of this thing right here with respect to x would be 3 times 1/3, which is 1, x squared y cubed dx plus, and the partial of that with respect to y would be x cubed y squared dy. That is an exact differential. This is an exact differential of that expression. That would be your f of xy. Okay? Now, if we say the m of xy is equal to this, the n of xy is equal to that, we've got our theory fulfilled. Okay? Now, notice if we make those identifications, then here's something to note. What is the partial of this m? This is our m. This is our n. What if we do the partial of m of xy with respect to y, not the variable that it is? Let's see what that would be. That would be 3 x squared y squared. And if we did the partial of n, the second one here, with respect to x, because that's the one not being derivative of that here, this would be 3 x squared y squared. Those are identically the same. And if that's the case, and this is what the next theorem is going to show, then that guarantees that you do have an exact differential. So here is theorem 2.4.1. The previous was definition 2.4.1. Here is theorem 2.4.1. Okay? Coming right up. Let m of xy and n of xy be continuous okay, and have continuous first partial derivatives PD is partial derivatives, okay, in a rectangular region R and this region R defined by x is going from A to B and y is going from C to D, period. Okay? Have continuous first partial derivatives in a region R defined this way. Okay? Then a necessary and sufficient condition and sufficient, okay, condition that m of xy dx plus n of xy dy be an exact differential is this condition right here. The partial of m with respect to y, not the one that is given there, has to equal exactly the partial of n with respect to x. If that condition's met, you have an exact differential and an exact differential equation if that's equal to 0. Now, they show the proof of the necessity here, and if you really want to go through it, I'll be glad to go through it with you. It isn't that difficult to follow, so I'll let you do that. The sufficiency part consists of showing that there exists a function f for which the partial of f with respect to x is m of xy, partial of f with respect to y is n of xy whenever that condition holds. The construction of a function f actually reflects the basic procedure for solving that, blah, blah, blah. So, here is how we go about solving these things. Now, it looks sort of complicated at first. It really isn't that bad. It seems somewhat circular at first. It's not really. It works okay. Here's what we do. Okay? Remember, one of the premises here was that your m of x, from the last slide or two that I did, that the function that is the exact differential for is your function f of xy. Okay? And how we got that set up was that the partial of this f with respect to x is what we call the m of xy. Okay? That's what our first premise is. Okay? Now, since that has to be true, what we're going to do is write that sort of in differential form, partial of f with respect to, differential form. Now, this is not quite what I consider rigorous, but it is. I'm going to change this to df and let this be m of xy, and then put this as our dx over here. Okay? And then I'm going to integrate both sides. Okay? Now, the integral of a perfect derivative, dl, which admittedly this wasn't, but just hang on to that concept. That is your f of xy. And what is that going to be? It's going to be whatever that integral is. Now remember, this is, now, trying to recall, I think both of you have had Cal 3. So you've taken partial derivatives before, which we've already been doing here. I didn't stop to mention that. But you've also done multivariable integration, okay? And that's what we're doing here. Okay, we're integrating m of xy only with respect to x. It's just like undoing taking a partial derivative. When we took a partial derivative with respect to x, say, we only take the derivative of the x part and treat the y as a constant. Well, when we're integrating m of xy dx, we're integrating with respect to x, so we leave the y's as if they're a constant and only integrate the x part. So that's what we have here. We have some, and whatever your m of xy is, you're integrating that with respect to x only. So that is, going to leave it just like that, m of xy dx, whatever that comes out being. But then, instead of a constant, we have some function, let's call it g of y. Because we're integrating only with respect to x, and we'll lose our x's that way, but we will still have y's. So that's going to leave us a the integral of m of xy dx is going to be in terms of y only because you're integrating out the x's, and then you'll have some constant g of y left over, okay? The arbitrary function g of y is your constant of integration. Now, what we're going to do, and this is the part that seems circular, almost, now we're going to take the partial with respect to y of everything on this side. So the partial of this with respect to y, the partial of this with respect to y, and this would just be the derivative of this with respect to y, because this has no x components. F does, your integral may, but in reality it shouldn't either, but we're going to put it there as if it were. And then say this partial with respect to this, remember the partial of f with respect to x was m, then the partial of f with respect to y is n of xy. So this isn't that far-fetched, this is just going by our original definitions. Okay, we know what the n of xy is. We know what the integral of m of xy is, and then knowing it, you know what its derivative with respect to y is, partial with respect to y. Okay? And that leaves us with, this is just what they call g prime of y. That's equal to your n of xy minus the partial with respect to y of your integral of m of xy dx. Okay. Now, this is the same as dg. I don't know why they changed. dy. And what if we do the integral of this thing here with respect to y? Okay? And integrate that. Okay? This gives us a g of y, and this is equal to the integral of n of xy minus whatever your partial with respect to y of the integral of m of xy dy, m of xy dx, sorry. These are all the thing you're taking the integral of by this one, and that's where your dy shows up here. Okay. Now, yeah. That's how you get your now. When you plug this g of y back into, I've already written over it, here's the equation, f of xy is equal to the integral right up here of m of xy dx plus g of y. Okay? Take this expression here, plug it into that g of y here, and then notice this. That entire expression here that you plugged in here, remember from the very beginning the f of xy had to be some constant because its differential was 0. So you set this thing here, this whole thing here, starting with this, doing that, plugging all this for the g, and set this equal to a constant. That's your constant of integration. Okay? Not that when you do any integrals you do a constant. That is your constant. Okay? Now, it's important to realize the expression, this n down here, this down here, before you put the integral around it. Okay? Oh, I'm sorry. This thing here has to be independent of x because it's a function of y alone. So that means where you had an x in here and you have x's in here, but these x's get integrated out and these have to be eliminated somehow. And that leads then to what our initial test was, that the partial of n with respect to x minus the partial of m with respect to y equals 0. That's just the original assumptions, that the partial of n with respect to x is equal to the partial of m with respect to y. Okay? Now, we could have started this whole thing not with this one, but with this one. Partial of f with respect to y has to be n of xy, and he comes down, you do everything you just did, and just now you're doing it with respect to y, and integrate with respect to this, integrate this with respect to y. Just go through the whole process, just interchanging basically your x, y, your n, m, that kind of stuff, and you could get it that way as well. Whichever method is easier. If one turns into a real ugly mess to integrate, try the other, okay? Either one of them should work fine, okay? And they give the all the formulas or equations for it, but then they go through all this and then say, but don't memorize these things, and that's absolutely for sure. Do the stuff. Don't memorize the equation, do the integrals, do the differentials, do the derivatives. Don't try to memorize the answer and come up with the answer all at once. Just do the work. Okay? Here's what I mean by that. Here's the first example. Example 1, page 67, top of the page. Here is an equation. 2xy dx plus x squared minus 1 dy is equal to 0. Okay. Before I proceed with this, I know we have been going just now 30 minutes. I need to run down to my office for just a moment, since no students are in here yet. I need to pick up something from my office. I'll be right back. So let me put this on hold. All right, I'm back. Sorry I had to take a brief break there. I had something in my office I needed, and I thought if a student showed up, I'd take a break then, but no students shown yet, so let's go on from here. Here is the example. Now, before we do anything else, we got to make sure it is an exact differential equation, okay? How do you do that? You take the partial of this, the partial of 2xy with respect to not x, but y, okay? And that's going to be 2x. Then we take the partial of your n, partial of x squared minus 1 dy with respect to y, with respect to x, because you take the partial with respect to the opposite variable, okay? And what's that? That's also 2x. And since both of these are equal, therefore it is an exact differential. All right, good. Well, then let's erase this. That was just to verify it wasn't an exact differential. They are identical, so therefore we can go from there. All right. Now, doesn't really matter which one you take. Let's just take the first one. This one right here, this is your m of xy. And how we got the m of xy, we assume there is some function, f of xy, it's equal to a constant. And when you take the partial of that with respect to x, this is what you should get. So the partial of f with respect to x should be 2xy. Okay? Now, kinda change this to f df is equal to 2xy dy. Okay, just doing dependence on y. Forget about the x's for a while. When you integrate this and integrate this, this gives you f of xy is equal to, we integrate this with respect to y, and that would be at x, because x is treated as a constant when you're integrating with respect to y, and the antiderivative of 2y would be y squared, okay, plus some g of y. Rather than having a constant, we do a function of y, because we're I'm sorry, I screwed that up. Okay, this was dx. Okay, I don't know where I got that. The last part was right. This is the first part that was wrong. Okay, you're integrating this with respect to x, dx. And this integrates to be x squared y plus some g of y. Okay? That's how that integrates. With respect to x is x squared y. Y is treated as a constant when you're integrating with respect to x. Okay? Now, what we're going to do with this is take the partial of this with respect to y now. Okay? So we're going to make sure I'm not skipping a step here. Yeah, take a partial with respect to y. And that will also take the derivative of the g, because that does not have any. So this thing is supposed to be partial of this with respect to x was your m, the partial of this with respect to y is your n of xy. This happens to only be of x, but that's okay. This should be your x squared minus 1. Not going to get there yet, but let's just say we will. That's what it should become. Well, what does this become? The partial of this with respect to y is merely x squared. plus g prime of y is supposed to be equal to x squared minus 1. Okay? Well, obviously the x squareds are the same on both sides, so this gives you dg dy is equal to minus 1. So that means dg is equal to minus dy, okay? Integrate both sides, and you get g is equal to minus y, okay? We take that and plug back in here, okay? Our original formula here was your f of xy is equal to x squared y minus y, okay? And that is equal to c, because f of xy is equal to c. Now, let's go back and check, and that's your constant of your, what do they call that constant anyway? The constant of integration. There is another word for our I guess that's as good as any. The word they use for it. Well, I can't see it right now. It's the family of curves, okay? That defines your family of curves, okay? Now, what you could do, if you did want to express this as an implicit equation, which you could, factor out a y here. No. Factor out a y times x squared minus 1 is equal to c, and then y is equal to c over x squared minus 1. Okay. Now, that happens to be an autonomous differential equation. It has several different ways you could look at it. But that is defined on any interval not containing either x equal 1 or x equal minus 1. Because if it did, this thing would be 0, and you wouldn't have much of a differential equation. You wouldn't have any of a differential equation. So this is only good for intervals not involving x equal plus 1 or minus 1. So anywhere from negative infinity to negative 1, but not counting negative 1, that would be fine. Anywhere from negative 1 to 1, as long as you don't count either one of those, containing either one of those endpoints, that would be fine. Anything from positive 1 to positive infinity, as long as it did not include positive 1. Now, the point they make here is this is not your solution. This is your solution. F of x is out of the picture now. That's just what you're aiming toward to set equal to c. Once you get what it is, don't use f of xy anymore. Okay. So that was a relatively simple one, which we could have done, I think, by separation of variables or autonomous. There's several ways we could have. This next one, however, no. This is going to be too complex to do any way except the way we just did. Okay? And here's what we got. E to the 2y minus y cosine of xy dx, so there's your m of xy, plus 2x e to the 2y minus x cosine xy plus 2y dy is equal to 0. Okay? Now, if there is a function that this is a differential for, then an exact differential for the left-hand side, then this is an exact equation. What's the test? You take the partial of this one, e to the 2y minus y e to the cosine. Yeah, that's ugly. Minus y cosine xy. You take a partial of that with respect to y and see what you get. So let's do that. That's going to be 2e to the 2y from the first term minus, here you have a product rule, so I'm going to do the first times the derivative of the second, which is going to be a minus sine of xy times partial with respect to with respect to y would then give you an x here. Okay, just so you can read what I'm doing here, because I started to put a C there, I needed an S. Okay, all right, there is your partial of the m of xy with respect to y. Let's do the partial of n, which is 2x e to the 2y minus x cosine xy plus 2y. Let's take the partial of that with respect to x, the other variable. Okay? Well, treat the y's as a constant, and you have partial with respect to x would be 2 e to the 2y minus partial of this with respect to y. X is treated as a constant. Derivative of cosine is minus sine of xy. Then the partial of that with respect to x would be y. So there's a y, and the partial of that last term with respect to y, there is, with respect to x, there is no x dependence. So here's the partial here. Well, here you have 2 e to the 2y plus xy sine xy. Yes, indeed. These two are the same, so you can proceed. Okay? So I'm going to erase this. All this was verifying you could do what we're going to do. Now let's actually do it. Okay. All right. Now again, it doesn't matter which one you go with, usually. Sometimes it does, big time. So the first one actually looks a little simpler. It's only 2 terms rather than 3 terms. It may not be, but let's choose that and let this be our m of xy. Of course, that's what it is. Okay? And we know that this should be your partial of f. Oh, let's write this down. F of xy is equal to some constant c. And this should be the partial of that f of xy. So partial of f of xy with respect to x should be this thing here. And this will be your e to the 2y minus y cosine xy. Okay? Now what we're going to do is wipe out our dx there and put it here. And we'll take the derivative of this and that. This gives you f of xy. Now the partial of this with respect, the integral of this with respect to x there is no x in here, so this is e to the 2y times x. Or I think I prefer to put the x in front so you won't get confused and think it's e to the 2xy. So let's put the x here. Okay, and again, the integral of this with respect to x, the y is treated as a constant. The antiderivative of cosine is sine, so that's going to be a minus y. Antiderivative is sine. Of xy, but you're undoing a chain rule here would give you a 1 over, because you're doing with respect to x, a 1 over y, so that wipes that one out. So here's what we've got now, plus some g of y. Remember, you got to have your so-called constant of integration. In this case, it's a function of y, which acts as your constant of integration. Okay. So that's what we assume our f of xy is. Okay. Because last time I had trouble finding it, I'm going to leave that alone for right now and take the partial of this with respect to y. And that's going to be the partial of this with respect to y. That's pretty ugly writing, but I hope you can follow it. This is with respect to y. This will be g prime of y. Okay. Remembering, this is supposed to be my n of x, which is n of xy, 2x e to the 2y minus x cosine of xy plus 2y. Okay, that is this partial of this f with respect to y should be that n. Well, let's see what we've got here when we do this. We're taking the partial with respect to y of this thing. Well, the x is not affected by that. That's just like a constant. And the partial of e to the 2y is e to the 2y with a 2 in front because chain rule. Okay? And partial of this with respect to y, derivative of y, that's going to be a minus cosine xy and we've got an extra x here because you're taking that with respect to y, so you have an extra x term there. Okay? And you've got plus your g prime of y, because I did the prime when I was taking the derivative of it. Okay? And this is supposed to equal 2x e to the 2y, which that term exactly does, minus x cosine xy, which is exactly what this term does, and we wound up with a plus 2y. Okay? So this tells us dg dy, that's what y prime is equal to 2y. So g is equal to y squared. We'll just leave it like that for now. Okay? right? Now, rewriting this then, your f of xy is equal to x e to the 2y. That's pretty ugly. Let me clean that up a little bit. Drop down half a line. My screen tilted on me. 2y. Yuck. Minus sine of xy plus y squared is equal to some constant c. That one, good luck trying to form that as an explicit expression of y. Can't do it, okay? That's going to be our solution. This is the solution. No g of y, no f of xy anymore. That's your solution. See what they got? They started with their partial of f with respect to y, and I don't know why, but they did. But the answer they came up with is x e to the 2y minus sine of xy plus y squared. I put equals c, they put plus c is equal to 0. One c is the opposite of the other minus the other one, so it really doesn't matter. All right. So there's example 2. Now, don't have time on me, so before we do example 3, let me just for a moment do this. 336, we go to 345. So let's go back. What happened to my PowerPoint? Here we go. All right. Let's see if we can squeeze number 3 in. So solve this equation. Whoops, because I did that, I lost my pen. dy dx is equal to xy squared minus cosine x sine x over y times 1 minus x squared, and y of 0 is equal to 2. All right. Now, looking at that, certainly not separable by any stretch of the imagination, not linear by any stretch of the imagination. Well, no. Okay. So, not much left to do with the tools so far in our tool belt, but to split this up this way. Multiply both sides by this, so you get y times 1 minus x squared. And by the way, you can just look at this problem and say x cannot equal plus or minus 1. And y cannot equal 0. Because of your original expression there, y can't be 0, x can't be plus or minus 1. Either one of those will make your denominator 0. Can't happen. Okay? Now, obviously, x can equal 0 because we got a problem there, thing there, and the y is not 0, so that's okay too. So here is your m of x. No, this is your, goes with the dy, is equal to xy squared minus cosine x sine x times dx. Okay? Now, rewriting that, and it really doesn't matter which way you do it. I don't think it matters at all. So what I'm going to do is write the first one down, xy squared minus cosine x sine x dx. I'm going to put plus because our form is always a plus there. Remember that? Always a plus. Go back to the original descriptor of it. It's always plus. M of xy dx plus n of xy dy. So you want a plus there. So that means we change the sign of this one. Y times x squared minus 1 dy. Okay? Because you're keeping this the same, moving this to the other side, that's going to negate it. I'll take care of that negation this way, and this is equal to 0 because you moved everything from one side to the other side, leaving 0 on that side. All right. First thing is this exact. Our test is the partial of this m, that's the m right there, xy squared minus cosine x sine x with respect to y. Is that equal to the partial with respect to x of y times x squared minus 1 okay, that's pretty ugly. Just making sure. There, I need those parentheses there. Now, what is that? The partial of that with respect to x. You treat the y as if it's a constant, so that's just there, and then to x. Okay? Well, let's do here. This is the partial of this with respect to y would be to y x, because that's all in terms of x's. And yes, these two are equal, so this is an exact differential. We can go with it. Okay, so let's erase these lines. These were just a test of the emergency radios. No, this is just a test, and it passed. So we know we can do this. Now, looking at this, don't know which way to advise you to go on it. Just looks like the second one is a lot simpler than the first. So why don't we try that first? The partial of your n with respect to, okay. Remember our assumption, now that we see that we can do it, that there is some f of x, y that's equal to some constant, that when you take it exact differential, you get that expression there. So that is implying that the partial of this f with respect to y, I'm going to take that one because it's a little easier, is equal to y times x squared minus 1. Okay, and I'm going to do away with the dy here and put the dy here, integrate this and that with respect to y, and basically you get your f is equal to, now, integrating with respect to y, this is treated as a constant, so that's a x squared minus 1, and integrating that with respect to y would be y squared over 2. Okay? So that would be what your f of xy would be, plus some function, and what do they use? H of x, I think it is. you could have that h of x sort of your constant of integration with respect to y, which means it could be a function solely of x. Okay. Now, what we want to do with this then is take the partial of this f with respect to x and see what we get. Okay? And that will be two x y squared over 2. So xy squared, okay, taking the partial with respect to x, plus h prime of x. Okay? Taking the partial of that. The y squared over 2 is just treated like a constant times x squared over 2 will be a 2 x will be its derivative. Derivative of minus 1 is 0. Everything else. So that would just be x y squared, okay, plus x prime, okay. Now, what we're going to do with that is integrate that with respect to x. Okay. I'm sorry. We don't need to do that. We've already done that on the other. Okay, let me take this off here. That was our f. Well, wait, I think we still do need to do that. Let me catch up. Yeah. So we do need to integrate this with respect to x. So let's do that. And this is x squared y squared. No, I'm sorry. X squared over 2 y squared, because we got rid of our 2 there. Okay. Plus antiderivative of h when you do this perfect derivative here. This is just h of x. Okay, and this thing is supposed to be your m of xy, because that's what partial of f with respect to x is. So that's wait a minute. Let me back up here a moment. Okay. When we're taking the partial of f with respect to x, that's what x is. This gave us our 2x y squared, okay, and the 2's cancel out, so it's x y squared. That part gives us nothing when you take a derivative of it, plus h prime of x. Okay. Now this thing is supposed to be your m of xy. So that's xy squared minus cosine x sine x. Okay, that's it. Okay, these two are obviously the same, so this says d h dx is equal to minus cosine x sine x. Tops. Okay, and let's put my dx over here. Okay, I think we're running out of time. So the h is going to be antiderivative of this is 1/2 cosine squared x. Okay? Is that true? Derivative of that would be 2 times 1/2 is 1. Cosine x times derivative of cosine x would be minus sine x. Yeah. So that's what the h is. Put that in here, and you get the f of xy is equal to x squared minus 1 y squared over 2 plus 1/2 cosine squared x. That's equal to some constant. So you can multiply both sides by 2 and you still have a constant. So our equation would be x squared minus 1 times y squared plus cosine squared x is equal to some constant. Oh, but we haven't used our initial condition yet. When x equals 0, y is equal to 2. So this will be minus 1 times 2 squared is 4, plus, when x is 0, cosine of 0 is 1. 4 plus 1 is equal to c, so c is equal to minus 3. So our solution is x squared minus 1 times y squared plus cosine squared x is equal to minus 3, or plus 3 is equal to 0. I bet you that's how they write it. No, they don't. They say, okay, first they say y squared times 1 minus x squared, so they've negated that one, and then negate the next one, and that would be a minus cosine squared, and then negate the next one. Yeah, it's the same answer, okay? And that one we could solve for y squared, not nearly necessarily for y, but for y squared, but we'll leave that alone. Now, I think we're out of time. Let me just see. Yes, we're 7 minutes over, but we're about 7 minutes late getting started, so that's almost works out. Okay? Now, where we're going to pick up next time is integrating factors, bottom of page 68. Okay? Let me put a mark in that place. And we almost finished 2.4, not quite. So homework exercises here, do any of the odds 1 through 19 that you find in the back of the book. In the ANS, page ANS-2. Now that we've done one boundary initial value problem, you can do any of the odds 21 through 25. They should be back there. We haven't done one like 27, so you don't need to worry with that, or 29 yet. Any beyond that. So we'll pick up and go. So just go through 25 for now, and once we do the rest of them, we will pick up and go from there. All right. I wish somebody were in here. I'd say any questions, but no one's here, so don't know if there's questions or not. So anyway, I'm going to shut it down and start saving